Alright, so we've already looked at the idea that you can get electrical force similar to a gravitational force. It turns out you can also look at the electrical force field around a single point charge as well. And so if you want to test that, and you have an electrical field there coming out from some sort of a charged object, you want to test the field in here, you could place a test charge there, and we use a positive test charge as the normal one, just so we actually have some sort of rules for which way the field lines are drawn. If you place a positive test charge there, you would measure the force that's actually acting on that test charge. There's that test charge there, and the amount of electric field strength would be the force acting per unit coulomb of a test charge there. Alright, and it's a positive test charge. So very similar to the idea of a force on a test mass. So it's really a definition that's not used very often in terms of calculations. It's also interesting to note here that you can do the same thing as with gravitational field over here. If you want to get the gravitational field around a certain mass, you can work out that by using the mass and how far away you want to go. So if you had a Van de Graaff generator sitting there and you wanted to work out what the field strength is at here, rather than actually place a test charge there, you can just work out what the source of the charge is, sorry, the source of the field is, and how far away we're interested in. So d squared or r squared down there, and again it's a constant. But you basically get the same sort of idea here. It's g, it's k, it's mass, it's charge, still the distance squared, and you do the same substitution. You would have put this this formula into here, and you'll find the test charges here that are placed out there cancel out, and you don't need to use them. Okay, and it's the actual source of the field here, the source of the charge here, Q or big Q, that would actually give you the formula. So it's often done as a big Q this as well if you read some of the textbooks. So you could use those three there, very similar to the way you do gravity. So we look at a PowerPoint on that here, and just play this here from the current slide. So as a definition, in the electrical field at any point is the force acting per unit positive test charge placed at that point. So we place a test charge there, you would measure the force on it in newtons, and you would measure obviously the charge that we're placing there, and it's the number of newtons per coulomb of field strength there. Okay, so that's the units there. If you're got an example and you placed a 2 coulomb charge there and found that it had 10 newtons, then the average is 5 newtons of force per coulomb of charge. So that's the definition of field strength, but not terribly useful when you're actually trying to do calculations. It is more useful to actually find the distance, the field at any distance from a source of the field. So if you look at one like that and you substitute, like I've just said, you'll end up with that formula that I've just been talking about. So substitute the force for electric force, and you'll end up cancelling the test charges there, little q's, and you'll end up with that formula. So that would be used in this sort of situation where you had a charge, had a distance, and they said what's the field strength at this point x. Okay, using that formula there, and that's on the formula sheet as well, so is the K. And there's a typical electrical field around a single point charge. So imagining you had positive test charges out here placed anywhere out here, they would be attracted towards that negative charge, so the field lines are drawn going towards the centre of that charge. So field lines for electric fields are always drawn towards negative point charges because of a positive test charge assumed out here. And if you had a positive charge there, then obviously they'd be repelling it to go the opposite way. So some examples will be to find the total electric field at point P here. So we had two charges here. So there is a field here due to the left-hand charge, and this is positive, so it'll be going away from it. It'll be going to our right at P. There's a field here surrounding this positive charge here, which is going outwards, so it's going left at point P. So you'll find both the fields in opposite directions here. So to get the total here, or the resultant, you would need to look at those two fields, work them out, and do a vector addition here, in which case you subtract them on a calculator because they're in opposite directions. So I would be doing it something like that. The electric field at the total here at point P is the field due to one of them, which is going to the right, that's due to these charges and these distances, plus the field going to the left due to the other one, with that charge and that distance. So this one here and this one here, and that should actually say 2, I've just realised, that's be Q2, and that should be D2, so that should be changed around. If you put those together, you'll actually find out you get this 1.6 by 10 to the 6 newtons per coulomb to the right. Sorry, 1.6 plus 3.6. So it's 1.6 by 10 to the 6 to the right, plus 3.6 by 10 to the 6 to the left. And don't forget to put in your as being micros as 10 to the minus 6, and that would be 10 to the minus 2. And you then got to do a subtraction on the calculator because they're going opposite. This is the bigger one, so the overall result will be to the left, the electric field. You can do some electric field diagrams here. Don't forget it's the direction of a positive test charge in the area. So positive charge on its own would be radially outwards from the centre of the charge. The negative one we've already seen. If you put them together, then you'll find that the total field in the middle here has to be an addition of both of them. So if you're looking here, there'll be a field going out away from one charge and towards the other. So really you'd have to do vector diagrams to work out what's the field going to do where they're overlapping here. So some rules about field lines. Just be aware that the arrows indicate the direction for a positive test charge on the field, and it's a tangent at that point that tells you the direction of the field, by the way. The closer together the field lines are, the field is stronger, the same as gravity. They only begin and end at the surfaces for conductors and so on, and they must meet the conducting surface at 90 degrees, not at an angle other than that. And they never cross over. Okay. The reason they don't cross over is because this is the vector sum of two fields. It can't be going in two directions at once. It's the total. It's going to have one direction as a total. So as an example of superposition here, this idea that the fields are the total result of the individual ones, you've got a field going out here away from the positive charge at this point. Fields going in towards the negative charge, so it's this way. So the total field here with the vector diagram tip to tail is to the right, which means that the field lines should be drawn off to the right at this particular point here. They should be a tangent to the right, and in fact you'll find all the way through here you get the same sort of result. They're all going to go to the right if these are equal charges. So here's a picture of one. So you can see here, if you did a tangential line here for each of those, then they'd all be going off to the right because of that vector sum. And you can see at other points that's the tangential line for this one here, but that again is a result of the field going out from the positive charge, and it's smaller because it's further away, and the field coming in towards the negative charge. Those two vectors for fields give you this total one. But that's the field for two opposite charges. In an exam I wouldn't draw as many diagram lines as that because it just takes too long, so you can probably get away with it, maybe 7 or 8 at the most, and still get a very good picture of what the field's doing, but that's a good diagram anyway. This is what they look like if they're opposite charges, and again it's the vector sum, and you can see in the middle here there's very little field, or should be zero field, because there's a field going to the right from the left-hand charge, going that way, and from the right-hand charge there's a field going to the left, which will be equal and opposite. They'll cancel, so it'll be zero in the middle here, but that's two positive charges. You get uniform fields by using parallel plates there. The edges you get some curving and non-uniformity there, but in the middle here they're nice and evenly spaced, parallel, so you're getting a uniform field or an even field. Okay. If you ever get your hair to stand up by touching a Van de Graaff generator, you'll actually find that the hair tends to follow the field lines, but it gets pulled down a bit by gravity, so it tends to curve, but it gives you an idea that there's a nice field off the head there. Okay, thanks.